Today we will be constructing a McCabe-Thiele diagram, which is a tool that allows us to calculate the liquid and vapor compositions of a binary feed. Come on. By using theoretical plates within a distillation column. So what we have here is a plot of our liquid composition versus our vapor composition of the lighter component. And what I mean by that is the component that has a lower boiling point / the component that is more volatile. So if we were to have, say, a mixture of benzene and toluene, benzene is the more volatile component. We would be plotting this for the benzene, not the toluene. So the first thing that we're going to graph out is a situation where our liquid component is equal to our vapor component, liquid phase of that component, rather. So this is an X equals Y line. This is a 50-50 vapor-liquid mixture of sorts. And what might be a bit more theoretical in nature is this line. Kind of make these two ends touch. And this is indicative of our vapor-liquid equilibrium. So when our vapor is in contact with our liquid interface, this is the line, the curve rather, that our compositions will be governed by. So now that we have these two curves, we can start by saying, well, okay, let me start at some higher point, some point on the higher end of this X equals Y curve. And we're going to have a downward slope, say something right like that, maybe about there, let's say, some random slope. For right now, we'll just deal with the random slope, but we will be calculating the slope of this line, which is known as the rectifying line. So this is the top portion of our distillation column. This is where we have distillate coming out. And so where this point meets the X equals Y, where this curve rather meets the X equals Y line, we go down and we say that this is the liquid component of our distillate. And over here, we have the vapor component of our distillate. So this is for our rectifying line. Now, another curve that comes into question. So let's say we start now on some lower end of our X equals Y line. And same thing, we'll say that this line intersects at some point here. This here is our stripping line. So these two are what we call operating lines. What we have here is our X equals Y line. What we have here is our vapor-liquid equilibrium line. These rectifying and stripping lines are our operating lines. And one final operating line we're going to draw out here. So we have rectifying for the top portion. We have stripping for the bottom portion. So maybe let's write this out. This is going to be liquid composition for our bottom, vapor composition for our bottom, B for bottom. Finally, what we have is we have a line that represents our feed. So this is our Q line that represents the composition of our feed. So let's go like about here. There we go. So this is a very general basis for our McCabe-Thiele diagram. And what we'll be doing now is we will be constructing equations using mass balances for each of these three lines. And we'll use an algebraic argument to determine why these vapor and liquid compositions line up with this intersection here. So let's just construct, I think might be a good idea. We'll just construct a very bare bones distillation column. So I'll start from the top here. Pick up on that. Thank you. So I have my top tray, technically. So we'll call this stage 0. And stage 0 is going to have some condenser coil. And so because of that, whatever vapor is coming all the way up through our distillation column will get condensed and start going right back down as liquid, and it'll cycle through our distillation column to get a pure product. So this at the very top here is our total condenser. And what happens up here, let me switch to maybe like this blue color, is that we have some liquid here. So we'll have a vapor phase up here. Use this. A liquid phase down there. So you see that this top stage is in equilibrium, and that's something that'll hold constant for all of our stages. And exiting, we will have some distillate stream. So this is our distillate. Now beneath that, is there a way I can copy and paste this? Yes, there is. Copy. Or duplicate. Hey, nope. Come on. There we go. So what happens now is that we have a very similar staging here. So now we're at stage 2, or stage 1. So this second stage, since we started from 0, this is technically our second stage, what we'll call this stage 1. And the reason we'll call this stage 1 is because this is going to be our first stage where it's purely just liquid and vapor in equilibrium with each other. So this is another vapor-liquid equilibrium here. What ends up happening is that the vapor from this stage will actually leave and go up into our stage 0, our total condenser. Similarly, we're going to have a stream coming down that is liquid from stage 0. So we're going to name this our liquid flow rate from stage 0, so L0. And this, our vapor leaving from stage 1, we'll call it the vapor flow rate of stage 1, so V1. And another thing that we're going to list in our nomenclature is that the vapor phase component of stage 1 we'll name Y1, and very similarly, our liquid phase component is going to be X1. So just to make sure that this is all kind of making sense, I'm going to get rid of this just so it makes a bit more sense to look at. Now, let's do another one of these. So duplicate that. Throw another one of these here. So a very similar thing happens here now. We have vapor going up, and it's kind of going to bubble through our liquid and pass out as vapor. Stage 2. And I'm going to put this a little higher because what I want to do here is I want to add in our feed. So add our feed. So might be wondering now, well, all right. Does it matter if my feed is bubbling through the liquid phase, or should we shoot it directly into the vapor phase? And the answer to that is go ahead, it's your pick, because essentially what ends up happening, so say if we had a 100% liquid feed and we poured it into our liquid here, well, all that liquid will just collect in stage 2 and leave in our flow to stage 3. So let me just keep on numbering these properly. whatever goes in, so if this is 100% liquid, liquid is going and collecting into our stage 2 liquid phase. It'll just collect and go down into stage 3. Similarly, if we had 100% vapor, that vapor is just going to collect here, go up as in V2, and bubble through our liquid phase here. So essentially, it doesn't really matter where we put our feed as long as we are consistent with the fact that our vapor travels up and our liquid travels down. We just got to stay consistent with that. So I'll add a couple more stages really quick here. Let's do it this way. I think this might be quicker. There, stage 3. And let's just do like here a stage 4. I think that's good enough. So we'll have stage 3, stage 4. So these similarly have their liquid phase and their vapor phase. I'm just going to do this really crudely so that I'm not wasting time. I'm making it look really pretty or whatever. So we have vapor flow 3 from stage 3, liquid flow from stage 3, vapor from stage 4. And what I'll have here now is our exiting stream at the bottom. So this I'll name B for our bottoms. So now you can kind of see this entire distillation setup. So we have our distillate at the top. So remember we had labeled our Y of our distillate, X of our distillate, our feed, we have that Q line, and we have the bottoms, which is this stripping line. And one thing that I guess might be good to also visualize is, I'll choose yellow, why not? When we're talking about the theoretical plates, that actually comes from this operating line and our vapor liquid equilibrium line. So what ends up happening is you draw these horizontal lines coming off of our operating line. So these are stages in our rectifying section. And once we cross over here, if it'll let me, we start going to our stripping line right about there. And maybe one more. I think I would fit like about one more stage here. Just about. So we have actually 3, 4, 5 stages. So I'll actually update this to represent that. I'll go one more stage just so that we're staying consistent. But as you see, these little triangles that we have created, that is a relationship between our operating lines and our vapor liquid equilibrium lines, actually represents the number of theoretical stages or theoretical plates that we have in our distillation column. So each of these little units actually represents a plate in a real distillation column. So we'll go one more here. Vapor from 5, liquid from 4. Got some liquid here. I'll finish numbering these too. So that's stage 5 over there. So we have Y5, X5, Y4, X4, Y3, X3. So now we have this kind of real life sort of representation of the theoretical plates that are defined by our McCabe-Thiele diagram. So the next step that we have here now is we'll go ahead and we'll use these values in a mass balance to help us construct the equations for our rectifying line, our stripping line, and our Q line. So let's point our attention to, let's just focus on, say, actually first, there are 3 big assumptions when it comes to making a McCabe-Thiele diagram. One is that our enthalpy of vaporization to vaporize each of the feed components is equal. for each component. Secondly, and this is one that's going to help us out, is that for every 1 mole of, let's say for every 1 mole of liquid evaporated, we get 1 mole of of 1 mole of vapor condensed. So if I have 1 mole of liquid evaporating for every 1 mole of vapor condensing back into liquid, what that essentially means, these two in combination, is that the enthalpy of vaporization is independent of composition, which further tells us that our vapor leaving a stage and the liquid entering a stage is equal, is constant throughout the distillation column. And the third one is that heat effects are negligible. Negligible. So these are the 3 big assumptions when it comes to McCabe-Thiele method. So if we were to say that, so basically what we're saying is whatever is entering our system. So let's say, well, I don't love that. Let's just go. So vapor, which is entering, let's say we're focused on, let's say stage 1. So V2 is our vapor entering our system, our stage. V2. And then L1, let's say, what is leaving our system is equal to whatever is left, which in this case, if we were to say V1 and L0, just maybe this will be better to. So V1 is our vapor entering. L0 is the reflux, technically. Whatever is entering minus whatever is leaving is whatever exits as our distillate. So this can also be rewritten as V2 minus L1 equals our distillate. And then V3 minus L2 equals our distillate. So you can say this for any single stage in our rectifying section, which I've moved our feed down to stage 3 over here, just in between cuts, so that we have an even number of stages in the rectifying and in the stripping. So all this is to say, for an overall mass balance in our rectifying section, is that our vapor minus our liquid flow rates is equal to our distillate flow rate. So this is for overall in rectifying. But remember that our McCabe-Thiele diagram is dealing with our less volatile component. So what could we say for that? Well, we could say that our vapor times our vapor mole fraction minus our liquid times our liquid mole fraction is equal to our distillate times our distillate liquid mole fraction. However, the issue with saying this is, remember when we did our nomenclature, whatever is entering our system is not the same number as whatever is leaving our system. They're different. These crossing streams are not labeled under the same nomenclature. So what we could say, we know that our vapor is coming from the stage above, from the stage below, and our liquid is coming from the stage above. So we could say, since we are increasing stage number and we're going down, is we'll say something like y, and we'll use a counter, so j plus 1 minus lxj is equal to the distillate times the liquid mole fraction in the distillate. So this is component based in our rectifying section. So now we have mass balances for the overall and mass balances on a component basis. So our next step here, we're going to follow along with our component-based rectifying mass balance. I'm going to divide across and isolate our y of the stage below. So that's going to be equal to, so our liquid over our vapor times our liquid mole fraction, or liquid component of phase above, stage above rather, plus our distillate over volume times our, distillate over vapor times our liquid component of the distillate. Now, one more thing that we can come back to, and I'm going to go back up here. So if we were to do a mass balance on just this, on this stage here, stage 0, we have an entering, we have an exiting, and another exiting. And we know that this liquid stream is constant, this vapor stream is constant, this distillate stream is constant because of the assumptions that come along with McCabe-Thiele. So the mass balance comes down to basically this, which if we were to rewrite it, we have our vapor is equal to our liquid plus our distillate. So plugging that in for our vapor now, we have yj plus 1 L over L plus D xj plus D over L plus D xd. Now, we can introduce something that's called the reflux ratio, R. So remember when I said that this L0, this liquid flow from stage 0, is something known as the reflux. And the reflux is this vapor coming up, condensing, and getting sent back down through the condenser. So this reflux ratio is a measure of how much liquid do we have versus how much distillate are we just running through our condenser. So in terms of the variables that we have, it's the ratio of the liquid we are passing through, how much of that is distillate that we're rerunning. So that's easy enough. I think the best way to do this is rearrange this L equals RD. Well, you could do it two ways. One way is that you could plug in RD for each time you see L and then try and get that, divide out the distillate and then have it done that way, or you can plug in L over D, and I think I'm going to go with that option. So I'll go divide this by distillate, divide 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 by distillate. So this L over D now we know is the reflux ratio as we defined it. Plus 1 is equal to reflux ratio over reflux ratio plus 1 xj plus 1 over reflux ratio plus 1 x of the distillate. And now we have a component-based mass balance for the rectifying section of our distillation column in terms of our reflux ratio. So essentially now what we have is the governing equation for our rectifying line, this line right here. And as you may remember, I stated that we have an algebraic argument for why this point on the x equals y plot is equal to our x for the distillate. And that argument is, well, okay, let's put in, so for that case, what we have is basically, what is x equal to the x distillate? So in that case, the vapor phase composition, or the vapor composition of this component rather, comes from the stage below, as we stated previously. So this is technically yj plus 1 over here, and then we have the distillate, which is just whatever is in that j stage. So if j equals 0, we have our y component 1 in our vapor incoming. So our distillate composition, so now we have r plus 1 times xd plus 1 over r plus 1 xd. And we see that we have a common term here. So we simplify this. R plus 1 over r plus 1 times xd. And of course, this cancels out to be 1. So we have yj plus 1 is equal to xd. So if our xj is equal to xd, then our yd correlates to that xd. And that correlation happens because at this point, our x is equal to our y, which is exactly what we're seeing here. Our x over here is equal to our y over here. So that's kind of an algebraic argument for why at the intersection of the rectifying line on the x equals y line, why that is equal to the distillate composition. So now let's go off and start doing the derivation for our stripping section of our distillation column. So let's take a look at the very bottom, stage 5 over here. It's a very similar thing to what's happening over at the top where we have our total condenser, but now at this point we have a bottoms that's exiting, a vapor that's exiting, and a liquid that's entering from the stage above. So we can go off and we can do a very similar thing. We'll write out a mass balance. So now in this case, we have our liquid entering, and that's going to be equal to our vapor that's exiting and our bottoms. But there is a bit of a nomenclature change that we have to have here. And it's very minor. It's just a notation thing. Whatever is below our feed gets a little bar to denote that these are streams that are going on below our feed. Not necessarily for the boil, the bottoms. That's just B. Yeah, I should have enough room. Okay, and then we can go off and we can do a very similar thing. We can have, so we have our liquid times our xj. So that's the stage that we are looking at. That, or rather, that's the stage above the stage that we are looking at. And then we have our vapor. Don't forget your bars. Our vapor times our composition from the stage we are looking at. So this is stage 5, this is stage 4. Plus our bottom times our liquid composition of the bottoms. Now, if you remember, at this point, we introduced something called our reflux ratio. And the parallel to that for our stripping section of our distillation column is called the boil-up ratio. And the boil-up ratio is going to be our V bar divided by our bottoms. So first, let's isolate our vapor composition here. So yj plus 1 is equal to L bar over V bar times xj plus B over V bar xb. And we'll use this definition to substitute for our L. So V bar plus B over V bar plus B over V bar. Oh, don't forget my xj. And we can now employ our boil-up ratio. So we'll divide everything by B. We'll do that in the blue color. So divide by B, divide by B, divide by B, divide by B, divide by B. So what we get now is our boil-up ratio plus 1 over our boil-up ratio x j plus our 1 second, let me exiting, that should be all right. And then 1 over boil-up ratio times xp. And this is our mass balance now for our stripping section per our lighter component. All right, slight sign error. When we plugged in, or when we isolated for y, we have to subtract this side over to that. So this is actually a subtraction sign. So these are all subtracted from each other. And that makes sense, and that's why I was hesitant to write this and why I was double checking my algebra, is because now we can do the similar algebraic argument for why our starting point for our stripping line is actually our bottoms composition on the liquid phase. So, or I guess bottoms composition in general on that x equals y line. So this is our governing equation for our stripping. This is our slope, this boil-up ratio plus 1 over the boiler-up ratio, times our composition minus 1 over boil-up ratio. This is our intercept over here. And if we were to plug in the case, so xj equals xb, it gets something like this, equals vb plus 1 over vb minus 1 over v or xb minus 1 over vb xb. And what ends up happening is that we subtract 1 on both sides on this numerator, and we get yj plus 1 equals vb over vb times x of the bottoms. This equals 1, so our y is equal to our x once again, and that satisfies this x equals y condition at the bottom. So at this point, we have derived the governing equation for our rectifying line. We have derived our rectifying equation for our stripping line, and we see where these two lines intersect is where we get our Q line, which is tied to our feed composition. So this is the next step in our derivation. So let's talk about this a little bit. So we're going to our feed stage here now. And we see that we have our feed here. Let's say it has some composition Z. We have a feed going in. We have our V bar coming in, our L bar exiting, our V exiting, our L entering. So essentially what we have is a way to relate our feed to our V and V bar and our L and L bar. And that happens in a very intuitive manner. So let me go over here, get some fresh, get a fresh spot to start writing. And let me just maybe redraw this out so it makes a bit more sense. Is it going to pick up on that? Nope. Come on. There we go. So we have our stage here. We have a feed entering. We have vapor exiting our stage. So this is V. we have liquid entering. This is all on the rectifying side of our distillation column, on the rectifying half. We have a V bar coming in from our stripping half, and we have an L bar exiting from our into our stripping half rather. So a feature of our feed is something we called Q. And Q is our feed quality. Feed quality. And Q is directly related to our liquid fraction, L fraction. Which is to say that if we had, so if our feed was 100% liquid, so 100% liquid feed, then our Q would equal 1. And vice versa, if we have a 100% vapor feed, Q would equal 0. If we had a 50-50, it would be 0.5. So again, we do a mass balance on our stage where our feed is entering, which is to say that, well, let's look at the liquid first. What's entering for our liquid? What's entering is our liquid from our rectifying half and our feed times the liquid fraction. So we'll say that L bar, which is what's exiting into our stripping half, is equal to our liquid from our rectifying coming in plus our feed quality times our feed rate. And we could say a similar thing for our vapor. We reverse these now because what's entering is our V bar. What's entering is our V bar and our feed, and what's exiting is our vapor going into our rectifying half, is equal to 1 minus Q times F. So basically, now what we have are two overall mass balances for this feed stage, which we can use to derive the equation for our Q line, which is kind of, I guess, maybe by design, Q and then Q line. So it's a bit more intuitive than it leads on. So the next step is to take this and start deriving the equation for our Q line. So now that we have these two equations, let's go back to what we have derived before in terms of our rectifying and our stripping mass balances. So for our, we'll start with the rectifying one, why not? For the rectifying mass balance, we said that our vapor, did we start with vapor? Yeah, cool. And for right now, I'm going to ignore these little j plus ones just because it's going to make a little bit more sense when we actually go ahead and do the entire derivation. So we go Vy minus Lx. Vy, I'm actually going to put Lx on the other side plus dxd. And then for our stripping, we had L bar x equals V bar y plus bxb. So L bar x equals V bar y plus bxb. Right? Should be right. Now, what I'm going to do is I'll add these two mass balances together to give me kind of an overall mass balance for the rectifying and the stripping. Because essentially what ends up happening here, let's go back here just to visualize this a little bit. We have a rectifying line and we have a stripping line. However, what we actually feed into our distillation column governs the rectifying and stripping lines, because that's what affects our reflux and our reboil ratios, our boil up ratios rather. So this Q, depending on our feed composition, is actually crucial to the design of our distillation column. And this is how we are able to get the governing equation for that Q line. So what we have now is Vy plus L bar X is equal to Lx plus V bar Y plus dxd plus bxb. Now, pointing our attention to just this, oh boy, we realize that dxd and bxb, we have our distillate coming out, we have our bottoms coming out. So if we were to do an overall mass balance, where is this? For this entire column, we see that what we enter is our feed, and what exits is our bottoms and our distillate. So we can bring that back to this mass balance here, and we say, well, if we're just going to have this these couple of terms here, we can combine them into our feed times our feed composition Z. So that's the first thing we're going to do here. The second thing that I want to do is point our attention now to these newly created mass balances that we have. And to point more attention to that, I'm going to highlight these two terms here. If we were to combine these two terms on one side, let's say I subtracted my L over to this side. So what we have now is L bar minus L times X. Well, if we were to do that here, L bar minus L is equal to QF times X. So we're going to have this equal to QFX. So we could do that here. Yeah. So I'll go QFX. And now we do the same thing here, where we have V minus V bar Y is going to be equal. So V minus V bar Y over here is going to be equal to 1 minus Q F Y. That looks right. So we're going to go plus 1 minus Q F Y. Well, now we look at this and we say, well, we say goodbye to our feed because that's in all three terms. And then we isolate our Y. So to do that, we will say, what's the best way to put this? So what we have left is Q times X plus 1 minus Q times Y. So is equal to Z. So I'll say that Y is equal to minus Q over 1 minus Q times X is equal, plus Z over 1 minus Q. And if I wanted to restructure this a little bit, we could say that we'll multiply this down here, say Q over Q minus 1 times X minus Z over Q minus 1. So now we have a third governing equation for our Q line, which is this line over here. So one last time, let's use an algebraic argument to prove that when x is equal to z, which is our feed composition, so now x is going to be equal to z, which is technically our xf, but for right now we have labeled it z. Not a big deal. Still will work the same. So now we have y is equal to our feed quality minus 1 times z minus, and I'm going to write it like this, 1 over q minus 1 times z. Well, now we see that we have z in both terms. So we have like terms, we can combine them. Y equals q minus 1 over q minus 1 times z. This obviously cancels out to be 1. And what we are left with is y equals z equals our feed composition, which is exactly how it is drawn up in the McCabe-Thiele diagram. And we have now successfully derived each governing equation for our rectifying, stripping, and Q line for our feed composition. And we have demonstrated how the McCabe-Thiele diagram allows us to calculate the compositions on the operating line using these three governing equations.